Ừ. Good afternoon to everyone. So this class topic is polar vortex. Okay. This polar vortex. Okay. So there are two words here, right? So one is polar, and second one is vortex, right? So what is the vortex first of all? And vortex all about and where it is coming from? Now, so I will explain. So vortex is basically this wiring. Wiring means like this. Wiring. Okay. Means something which moves in this like this circular motion, right? So for example, whenever you take some lots of water in your bucket, right? So up to here, bucket water, okay? So or your kitchen sink also. So you can try, you keep widening. So what happens there is this hole, like it's created like this, right? So this is a whirlwind. So whirlpool that is created even in your washing machine, right? So you can find in your washing machines also. So what happens? Right. So that is called vortex. Okay. That is called vortex. So vortex is a whirling action. So now what is this whirling action and how it is related to polar areas? So that is where this creation of polar vortex happens, right? So then next, now second one is polar. So polar, which means anything related to north and south pole, right? So now, so what we understand, the term polar vortex is that there is circular movement, right? Circular movement of air, a wind occurring in both poles, that is North Pole and South Pole. So it always access near the pole. So let's understand this concept in terms of this entire climatology or entire climate system. So now you just imagine, you see here, so a ball is spinning, right? Ball is spinning a speed of how much? 1,000 miles per an hour. The air surrounding this balls also spins, right? So in addition, the air spins much more at the these edges, like this edges of this ball. So in reality, this ball is the earth, right? Like this. Okay. So these edges of the balls are the poles. So this is North Pole and this is South Pole. So and the air spinning at the poles is actually the polar vortex. So the earth rotates from west to east. So you see here, this is north and south, east and west. Okay. So the earth rotates from where? Where to where? West, from west to east. Okay, like this. And so does the air. So, and the polar vortex also rotates from west to east at about how much? 150 miles per hour speed, right? So the polar vortex, if you go in the northern America or Europe or maybe Australia, you might hear the terms of this polar vortex or polar blizzard very often in the winter, which brings in bad weather, including some zero temperatures and lots of snow. So now let's see what is polar vortex. So actually, there are two vortices on the earth, right? So first one is southern hemisphere. This one. And so it is over the Antarctica, and northern hemisphere. So that is over the Arctic region, right? Arctic region. So the northern hemisphere polar vortex is the stronger one, right? Northern is the stronger one because so the winds in the southern hemisphere are less effective, right? So due to the effective has southern hemisphere has less land. So that is northern hemisphere. So this kind of unevenness of land surface causes changes in temperature and pressure, right? So that further has tremendous effect on regional air and winds. Okay? So now you see here, the northern hemisphere is about 60.7% water and 39.3% of land is there. The next in southern hemisphere is about how much? 80.9% of water and 19.1% of land. So in you compare these hemispheres. So from the land is how much is there? In northern hemisphere 39.3 and in southern hemisphere only 19.1% land is there. So that is the main reason. So now when you say about the polar region, for example, let's go the North Pole. Here you will find the polar vortex in the upper level, right? Upper level of the atmosphere. So in other words, you will find this circular movement, right? This circular movement of wind in the upper level of the troposphere, or it is an upper level low pressure area lying near the Earth's poles, right? Near the those are north and south poles, right? So if you can remember, there are 4 layers of the atmosphere, right? So all of you know about that. So what are the troposphere, stratosphere, and also mesosphere, and lastly thermosphere. So these 4 layers of the atmosphere is important. So before previous class, I have told about this, right? So a polar vortex starts from the upper troposphere and it extends into the stratosphere, right? And sometimes that is continuous up to the mesosphere, right? So, if you notice the ozone layer, all of you know about the ozone layer, that existing beginning of the stratosphere, right? So the in polar vortex occurs in the upper level of the polar regions atmosphere, right? So that is, it starts in the tropopause and it extends up to the stratosphere, right? So now the next one is know that the polar vortex is an area of low pressure. Low pressure. So now you may have a question, how come there is a low pressure in polar regions? Right. So now we always know that low pressure is an area of less. Okay, right. Less dense air. So with warmer air temperature, right? So then how come there in polar regions? So now, and the poles are very cool as there is less sunlight, right? All of you know. And the poles are naturally very cold, especially its air, right? So a polar vortex is actually a large area of low pressure and cold air. So that rotates eastward around the poles, right? Like this. And so eastward means that the air moves counterclockwise, right? Counterclockwise at the North Pole and clockwise at the South Pole, right? So the northern hemisphere, it is an anti-clockwise. It means like this. Okay? And in southern hemisphere, it is clockwise. Sorry. Like this. Okay? So this is the northern hemisphere and southern hemisphere is clockwise. Okay? Like this. So this kind of wind movement, very fast wind movement happens at the poles, specifically in the stratospheric belt, that is upper atmosphere here. So that is important, right? So now what happens often during winter in northern hemisphere? Remember, now it is winter in northern hemisphere, right? So when we say, it means sun's movement is southwards, right? Southwards. So this is oscillation that leads to this here, right? So the polar vortex becomes less stable, means less stable and expands. What will happen? So the cold air will come to these land areas and it will brings lots of chilly winters, negative temperatures, right? So this is why it was concern for many of the countries like Canada, US, etc., right? So that this keeps happening in certain years where there is this polar vortex migration to these those land areas, right? So now, that how this entire polar vortex is formed and how it functions, why it is important, right? So now you see here, the first time it was discussed even in as back as 1853, right? So just wait. 1853 in an article that is Living Age. So where it was discussed as a fact that, so this also happens. So this kind of phenomena is there where you have upper atmosphere circulation, which is kind of whirling, this whirling wind, which is there at the poles, right? So now, so let's discuss this in terms of the conceptualization and information, right? So now so many people get confused at how this low pressure system is formed in the polar areas. How? So now I will explain. So why this polar vortex is created as low pressure system and how even if there is so much of holding. So now let's understand what happens here. If you observe what is happening, this is the line which is called as tropopause, right? This is tropopause. So which is about 12 to 15 kilometers here. 12 to 15 kilometers. This one. Okay. Now, and it is the dividing line between this troposphere and the stratosphere, right? That is tropopause. So the polar vortex starts at the upper troposphere. So this is troposphere, it is stratosphere, and middle of the tropopause, right? And it extends into the stratosphere. So, and sometimes it is continue up to the mesosphere, right? So what happens? This height continuously keeps going down. You see here? As we go towards the pole, North Pole. So at the pole, the tropopause is about 8 kilometers. I think here, this 8 kilometers, that is between 7 and 9 kilometers. 7 to 9 kilometers. So, and it is maximum about 15 kilometers here. You see 15 kilometers at the equatorial, this equatorial region. That is the basic idea, basic structure, right? Now, what happens? The air from this ferrule cells. This ferrule cell and the polar cell, right? This polar cell. So this is the easterlies. You see here, this is the easterlies and this is the westerlies, right? So it meets this junction here. This is the junction, okay? So that is the, you see here 16 degrees north, right? 16 degrees north. So this is called polar front, polar front. So, and also what you find, there is a polar front jet stream that is created here, right? So because of this mixing of warm and cold air, right? Mixing of warm, this warm and cold airs. This is the polar front, right? So we have discussed this kind of front formation. So this is warm air and this is cold front, right? So, and this is the 60 degrees north. where jet stream is formed, right? So which is called polar front jet streams also, right? So now when we are discussing this formation of this particular polar vortex, let's understand how it is created and why it is a low pressure system. Why we say that, right? So now you see here, because what happens in why it is low pressure system, that is not the low temperature, lower temperature. It is the upper atmosphere. The upper atmosphere. So it is about a troposphere, right? So it is in the stratosphere and many times also extends up to where? Up to stratosphere, exosphere, right? So now when you see this warm front, it is obviously will go up here, right? Here. And cold front will dominate here, right? So that is what warm and cold have this property. So what happens, one branch of this actually going here and subsiding down. But you see this particular image here, okay? Here. Same figure, this figure is taken from here, okay? So this circulation, right? This circulation happens in this particular area, right? So it goes up and then subsides down here, down on the pole, that is the North Pole. That is where it is high pressure, right? High pressure. So, but another branch reaches tropopause, right? This tropopause. And it goes upper atmosphere circulation. So, which is warm air, right? Which is warm air. It's called warm air. In nature, in context to polar area, right? So, this warm air, which is relatively warmer than what you have cold air in the lower troposphere or atmosphere, right? So this warm air obviously rise up and it will go the polar vortex, right? Polar vortex. Okay. This polar vortex belt. So where it will starts doing like this, right? Like this circulation or wiring or circulation action due to Coriolis force. It means strongest where at the poles. So if Coriolis force is strongest at the poles, that warm air that raise up, it will starts rotating counterclockwise like this, right? So in where? Northern hemisphere only, right? So that is how this polar vortex is formed, and that is important to understand the formation of the polar vortex, right? So what happens here? The formation of polar vortex is that warms, you see here, warms air front that rises up, right, in the upper atmosphere, and the one branch is actually subsiding. This here, subsiding down. So one branch is going up, right? So the tropopause is the dividing the line, right? So that's why some are get confused that even if it is a North Pole, why this low pressure? So this low pressure is because of this warm air front, right? Warm air front that goes up there. And in context to this area, it is actually relatively more down, right? Relatively. So more warm because the ground area is far cool, right? So that is the reason. So relatively it is warmer. So that is why it is low pressure. It is low pressure. So, and where this low pressure is sitting, it is sitting on the lower atmosphere, which is high pressure, right? So this polar front jet streams which keeps guiding it, right? So now, you see here, so what, why what is fixed to this, why fixed to this pole here? And why is not moving like here and here and here? So remember, there is a guard here. This is it's called guard. So there is a gate here. That is polar front jet, right? Polar front. Or polar front jet stream. So it is like a guard. So it is like a gate which does not allow this polar vortex to move away. So it is fixed in this particular zone only, right? So, but remember, at times when this guard is sleeping, what will happen? So, for example, in your apartment or any in your other place or offices, so in night duty guards, security guards, when they are sleeping in duty times, so what will happen? So some thieves are sneaks into those areas, right? So when this weakens, so when the weekends, remember the jet streams. So jet streams are also weekends at certain time period, right? So that is when this polar vortex gets time to actually intrude into certain areas where you find difficulty in the Midwest US. You see here like this. Okay. You see here. So Midwest of US and the Canada. So where lots of cold winds and negative temperatures are there, right? So you observe these two particular diagrams where you have stable here, stable polar vortex, right? That is this one. And you have strong, sorry, it is a strong jet stream, right? It means these positions are fixed here like this. So this is the guard, right? So now these positions are fixed here in strong or stable polar vortex. So it is there clearly on the northern pole, right? So and it is now guided or bounded by this guard, like this. This guard, okay? So that is strong jet stream, this strong jet stream, okay? So this is a normal situation, stable situation, right? Now, but at times when there is weakening in the jet stream here. So when this is loosening up here, like this, okay? Because you understand that there is a continuous north and southward shifts here, okay? So of the insulation and temperatures will shift, right? So accordingly, pressure will shift, right? Pressure will also shift. So, and remember, jet streams is formed because of the drastic difference between these air masses, like air masses. So, because of the that this also weakens, right? Weakens at times, and when it weakens, what happens? This cold air moves here, like, right? This arrow mark, okay? Cold air moves southwards, towards southwards, that you see in this particular pictures only, right? Like this. So you can observe here also, like this, okay? So this is the stable. You observe this one. Here, you see here, like this, okay? So that waves called Rossby waves, R-O-S-S-B-Y waves. So when these Rossby waves, these calls are Rossby waves, okay? These waves are the weekends, right? It cannot contain this particular air, right? Particular air, this particular air. So, and it starts going down, and that is when there is starts a problem, right? And that is where, because of this polar vortex oscillation. So according to this Arctic oscillation, as we say, it starts happening. It starts happening. So this is where it impacts the land area. And you see here, these land areas. This is expanding. Expand here. These are the expanded areas, land area. Right? So this is entire Canada and Midwest US. So it had lots of freezing temperatures here, and beyond freezing temperatures that leads to lots of trouble, right? So polar vortices are weakest during summer and strongest during winter. So remember, jet streams also is stronger in winter, right? So, and it is weak during this particular time period when you have in summer. So what will happen? Obviously, when you have weakening and against strong thing happening there, that is a fluctuation. So there is an oscillation. So during this anomaly, during fluctuations, this expands, and many times you find that due to this weak jet streams, there is a cold air that rushes from this polar vortex, creating these small pods in particular areas, these expand areas, right? So these small pods that are entering these entire anomalous system that leads to lots of trouble in the land areas, which is dangerous in terms of situations, right? So now another one is ozone depletion, right? So ozone depletion, so the polar vortex is largely in stratosphere, right? Stratosphere. And remember, the stratosphere has maximum concentration of this ozone, right? So what happens in the Antarctica polar vortex? Antarctica polar vortex. So let's understand the chemistry of the Antarctica polar vortex has created severe ozone depletion. Severe ozone depletion. So remember, Antarctica has lots of ozone holes, as we know, right? So nitric acid in polar stratospheric clouds. So now, remember, these polar stratospheric clouds have nitric. Is that nitric as what is that? Nitric acid composition, right? And nitric acid composition that is react with these chlorofluorocarbons to form what is that? Chlorine. So nitric acid reacts with fluorocarbons, that is to form chlorine. You see here. So here, chlorine is formed here, right? So if you see here, what is happening? So this 70 degrees, right? 70 degrees south. So that is close to the where poles, right? Poles, these poles. So if you find chlorine here, chlorine concentration actually, you see here from here to here, it is increasing, okay? Increasing, right? So what happens? The chlorine concentration build up during the polar winters, right? So in the polar winters, chlorine concentration rising due to this ozone. What is that? Ozone destruction. Ozone destruction. So that is starts happening when there is sunlight that returns in spring, right? So these clouds can only form at temperatures which are below minus 80 degrees centigrade or minus 112 degree Fahrenheit, right? So remember, when reaches that acute winter temperatures of minus 80 degrees centigrade, so that is when this chlorine composition leads to this depletion of ozone, right? And since there is a greater air exchange between the Arctic and the mid-latitudes, and ozone depletion at the North Poles is much less severe than at the South Pole, right? So Northern Pole has lots of mixing of air, right? So because of this land and ocean distribution, but because so much of land area is not available in Southern Polar nearby, right? So not much of exchange of air happens, right? So mostly that concentrated air in the polar vortex, that is remains there. It does not change as it changes in the northern hemisphere. So that's why due to this persistently remaining chlorine, right? This chlorine. Right? So actually that leads to more ozone depletion in the southern portion than in the northern portion. Right? Now, so accordingly, the seasonal reduction of ozone levels over the Arctic is usually as, what is that? Ozone dent. Ozone dent. So remember, there are two terms in southern hemisphere. What is that? So that is in the Antarctica belt. Antarctica belt. It is called ozone hole. Right? So because it is larger, while it is just called a dent ozone. Dent ozone. So dent in the northern hemisphere, right? Or in the Arctic belt. So that is the main reason here. So now you remember that how this polar vortex phenomena is also related to ozone depletion. So that is another important point. So now this is the polar vortex phenomena. It impacts and its creation, right? So now you see here. Okay. So now you observe this figure. This is the ozone depletion process. Ozone depletion process. So the ozone depletion process begins when chlorofluorocarbons and other ozone depleting substances. So that is called ODS, right? ODS. So those are emitted into the atmosphere. And second one is, you see here, winds efficiently mix the troposphere and evenly distribute the gases, right? So the chlorofluorocarbons are extremely stable and they do not dissolve in the rain. So after a period of several years, these ODS molecules reach the stratosphere. About how much? 10 kilometers above the Earth's surface. Okay, 10 kilometers. So now the third point is the strong ultraviolet rays, right? Ultraviolet light or rays or breaks apart this ozone depleting substances molecules, right? So the chlorofluorocarbons and hydrochlorofluorocarbons and carbon tetrachloride and methyl chloroform and also some other gases. So those are released chlorine atoms, right? Chlorine atoms and halogens and methyl bromide release bromine atoms. Methyl bromide releases bromine, right? So the next fourth one is here. So it is these atoms that actually destroy ozone, right? So not the intact ODS molecules. So it is estimated that one chlorine atom can destroy over 1 lakh ozone molecules before it is removed from the stratosphere. Okay. So now fifth one is depleted ozone allows more ultraviolet radiation to pass through the atmosphere. Okay, pass through the atmosphere. So, and then next we are going to next point. So more ultraviolet radiation can causes more skin cancers, right? More skin cancer. So some of the ODS and including chlorofluorocarbon and hydrofluorocarbons and also carbon tetrachloride and methyl chloroform. So these are release, what is that? Chlorine atoms, right? And others ODS and including halones and methyl bromide. So those are released what? Bromine atoms, right? So it is there, these atoms, these chlorine and bromine atoms that actually destroy the ozone, not the intact ODS molecule, right? So it is estimated that one chlorine atom, you see here, so one chlorine atom can destroy over how much? 1 lakh ozone molecule before it is removed from the stratosphere, right? So the biggest problem was chlorine from a man-made compound that is called chlorofluorocarbons. Okay. So on the ground, chlorofluorocarbons are not harmful, but once they float up to the stratosphere, the sun breaks. The sun breaks them, that is down into, what is that? Chlorine, this chlorine, okay? So they bind with ozone to make oxygen and chlorine monoxide. Then the loose oxygen atoms bump the chlorine atom out, right? These chlorine atoms out. Right. And freeing it to destroy more ozone molecules here, right? So, and that causes a chain reaction. So, the long lifetime of the chlorofluorocarbons is a bigger part of the problem. So, they live anywhere between 50 to 150 years in our atmosphere. You see, like this. Okay. So in 1987, ozone levels had dropped by 50%. How much? 50%. So this growing threat lead to some of the fastest collective actions on the climate you have ever seen, right? So now, after the chlorofluorocarbons ban, we began using hydrofluorocarbons, right? So these hydrofluorocarbons do not deplete the ozone layer, but they are a potent greenhouse gases, right? So that contributes to the climate change. So since in the year of 2016, the Montreal Protocol was amended to include hydrofluorocarbons, and now they are being phased out too. But they're only one part of a large issue, right? Now, why ozone hole, especially in Antarctica or the South Pole? So now, what is the reason? So in the year of 1995, so scientists discovered a massive loss of ozone layer in over Antarctica. This ozone layer, right? Because you know, the all one factor is the chlorofluorocarbons. So these are producing the reactive chlorines, right? Chlorofluorocarbons producing the chlorines, right? Chlorine. So that breaks down ozone, right? So, but where do those chlorofluorocarbons come from? Well, they are all over the world. So they come from mainly, what is that? Air conditions. These are the mainly air condition. So they are all over the world and are all over the earth. There are chlorofluorocarbons in the atmosphere. So that includes over to us, right? So the very low winter temperatures in the Antarctic stratosphere, it causes polar stratospheric clouds. That is called PS, sorry. PSCS, polar stratospheric clouds, that is too far. And special reactions that occurs on these PSCS combined with the relative isolation of polar stratospheric air and allow chlorine and bromine reactions to produce the ozone hole, right? Ozone hole in Antarctica springtime, right? So the formation of ozone hole in the Antarctica has been an annual occurrence and it has been recorded for the last 40 years. And human-made chemicals. So this is the main important. Human-made chemicals migrate into the stratosphere and accumulate inside the polar vortex, right? Polar vortex. So it begins to shrink in size as warmer temperatures dominate. So the Antarctica ozone hole, one of the deepest, largest gap in the ozone layer in the last 40 years. Remember this, last 40 years. So now it has closed right up. So according to World Meteorological Organization, WMO. So in the year of 2021, January 6th, 2021, January 6th, it has closed, right? So the annually occurring ozone hole over the Antarctica, and it had rapidly grown from mid-August and peaked at around 24 million square kilometers. So one of the largest so far in early October 2020. So the expansion of the hole, it was driven by a strong, stable and cold polar vortex and very cold temperatures in the stratosphere, right? Stratosphere. So the same meteorological factors also contributed to the record of 2020 Antarctica ozone, which has also closed, right? So the polar vortex is a wide expanse of swirling cold air. A low pressure area in polar regions. So during winters, the polar vortex at the North Pole expands and sending cold air southwards, right? So an ozone hole is the thinning of the ozone layer boosted in size by colder temperatures. As the temperatures high up the stratosphere, that it starts to rise automatically and ozone depletion slows. So the polar vortex weakens and breaks down. So by the end of the December, the ozone levels return to the normal. So this time around, however, the processes took longer, right? So the 2020 Antarctica hole was unprecedented as the polar vortex kept the temperature of the ozone layer cold, preventing the mixing of ozone depleted air above the Antarctica with ozone-rich air from higher latitudes, right? So, you see here some of the pictures in variations of the ozone hole. So this is the ozone hole in the year of 1917. So there is no hole, say only small little bit, right? Here. So the next 1999, you see here this blue color indicates ozone hole. So 2019. So this is the 2019 hole is the smallest record on the hole, right? So abnormal weather pattern, right? So in the upper atmosphere over Antarctica, dramatically limited ozone depletion in what is that September and October 2019. Okay, so that is resulting in the smallest ozone hole since 1982. So this report from the NASA and NOAA, right? So the annual ozone hole reached its peak extent of 16.4 million square kilometers on September 8th, 2019, right? And then shrank to less than 10 million square kilometers for the remainder of September and October. So during these years, with normal weather conditions, the ozone hole typically grows to a maximum area of about how much? 20 square kilometers. 20 square kilometers. So it's a great news for ozone in the southern hemisphere, said Paul Newman. Paul Newman. So you see, P-A-U-L, Paul Newman. So he's the chief scientist for Earth Sciences at NASA, right? NASA Goddard Space Flight Center. So he says, but it's important to recognize that what we are seeing this year is due to warmer stratospheric temperatures. It is not a sign that atmospheric ozone is suddenly on a fast track to recover. So this sentence about says this Paul Newman, right? So, and next we are going to large and deep Antarctic ozone hole in the year of 2020. So persistent, the cold temperatures and strong circumpolar winds that is supported the formation of a large and deep Antarctic ozone hole in the year of 2020, and it is likely to persist into November, right? November. So this is October, right? October, no, September, right? September 8th, and this is also September 20th. So the annual ozone hole reached its peak area of at 24.8 million square kilometers That is 9.6 million square miles. So it is roughly 3 times the size of the continental United States. Is that continental United States? So scientists also detected the near complete elimination of ozone for several weeks in a 6 kilometers, right? That is 4 miles. So 6 kilometer high column of the stratosphere near the geographical, the South Pole, okay? South Pole. So reasons for the ozone hole. What is the reason? Anybody? Okay, I will see. So the ozone hole has developed because people have polluted. What is the main reason? People, humans, right? So the atmosphere with chemicals containing chlorine and bromine, right? So that is the main thing, and that is the main reason. So the primary chemicals involved such as chlorofluorocarbons and bromine, and also other related halogen compounds and carbon tetrachloride, and also nitrogen oxides, right? So chlorofluorocarbons in particular, they have been used for a wide range of applications, those are including refrigerations, air conditioners, and foam packaging, and also making aerosol spray cans, right? So these are the reasons. So because these chemicals are so inert, so they are able to stay in the atmosphere, that is long enough to be carried upward to the stratosphere, where they can damage the ozone layer. So the actual processes by which chlorofluorocarbons, so they destroy ozone, are complex and require certain weather conditions to exist, right? You see here more ozone here and picture and less ozone. Okay. The next warmer of the year. So this is the record and cold year. Now we are going to ozone depleting substances. So just a second. So now ozone depleting substances, that is called ODS, right? So it is generally contain chlorine, fluorine, bromine, carbon, and also hydrogen in varying proportions. And those are often described by the general terms halocarbons, right? And chlorofluorocarbons and carbon tetrachloride and methyl chloroforms. So these are important human-produced ozone depleting gases. So that have been used in many applications, including refrigeration, air conditioners, and also these foam blowing and cleaning of electronics compounds, and also as solvents, right? So another important group of human produced, those are halocarbons. So is the halogens, so which contains carbon, bromine, fluorine, right? And chlorine also. So and it have been mainly used as fire extinguishers, right? So now these substances are effective ozone depleters for two reasons. So what are those reasons? So now you see here, the first is that they do not break down in the lower atmosphere. So they can remain in the atmosphere from 20 to 120 years or more. So unlike the most chemicals released into the atmosphere at the Earth's surface. So, and ozone depleting substances are not washed, right? Are not washed back to the earth by rain or destroyed by other uh, chemicals, right? Other chemicals, which means they drift up into the stratosphere, right? The next second one is that they contain either both chlorine and or bromine, and does help the natural reactions. So that destroy ozone, right? Ozone is the main reason. So once they reach the stratosphere, this ultraviolet radiations break up these molecules into chlorine or bromine, right? So which in turn break up O3, ozone, right? So these are the two substances are effective ozone depleters. So next class, I will tell you, so what are the ozone depleting substances, right? So those are chlorofluorocarbons, and hydrochlorofluorocarbons and hydrobromofluorocarbons and halogens, methyl bromide, carbon tetrachloride, and methyl chloroform, and also bromochloromethanes. So these are the ozone depleting substances. Those are chemicals that destroy the Earth's protective ozone layer. So these are included here, right? So use of ozone depleting substances. So what did we use ozone depleting substances for? The main uses of ozone depleting substances are including chlorofluorocarbons and hydrofluorocarbons in refrigerators. They are using in refrigerators and air conditioners, and refrigerants in commercials, right? And also hydrofluorofluorocarbons and halogens using in fire extinguishers and chlorofluorocarbons and hydrofluorofluorocarbons and using in foam, and also chlorofluorocarbons and hydrofluorocarbons. So those are as using aerosol propellants and methyl bromide. Methyl bromide for fumigation of soil and structures and goods to be imported or exported. So they are using in these applications, right? So in next class, we will discuss these are one by one. These ozone depleting substances, right? Carbons.